Hi class, this is our second lab and I have put together a video to help you understand this lab. This should be a review regarding density. If you do not understand density, there's section 1.9 goes over that. Also, you should have access to your textbook, ebook from Chem 10. You definitely would have covered it there, and if not, the internet has many lovely videos and readings to help you understand density. So let's get started. So let's first go over chemistry lab equipment. And some of you guys may have been in a lab before COVID broke out. And I'm not sure when exactly now, everything's a blur. But a beaker is right here. And it is what you usually use to, excuse me, to hold solutions, reaction mixtures during experiments. Same goes for Erlenmeyer flasks. So it's one of these two that you will usually use to hold your solutions during an experiment. They are very low volume accuracy, meaning don't ever use these graduated lines. They are estimates only estimates. If you didn't need an accurate amount, then you could definitely use it. But if you're doing an experiment that requires a specific amount, this is not the way you want to go, because you're already basically messing up at the beginning of a lab, and it's not going to get better after that, no matter how much you try to fix it if you're going off of using wrong equipment. That is what some of this lab is about today, is to use the correct equipment and then see which one is actually better for an experiment. So Erlenmeyer flask, beaker, these are what we would commonly use. Think of it as a pot. If you're cooking, this is what or a pan. We're always going to use these, but you don't just pour water into them. You use measuring cups. You use something that's going to give you an accurate volume for a recipe. Now, another thing is that we're going to cover are high volume accuracy equipment, a pipette or a graduated cylinder. You tend to have graduated cylinders in your drawers if you were in lab in person. Pipettes you would have out if the experiment called for them. Pipettes are a little harder to use, so we're going to jump over to graduated cylinder first. A graduated cylinder measures and transfers multiple different volumes of liquids. It's got a high accuracy, but you need to also make sure that you're using the correct graduated cylinder. So for instance, if you needed to use 39.5 mils, you would grab a 50 mil graduated cylinder. They come in different sizes. There's 10 mils, 25 mils, depending on your lab and what's given to you. You would never want, or you would try to want to avoid using something like a 50 mil graduated cylinder for a 10 mil or a 15. You want to keep them closer to the volume amounts. It's just a little bit better. Another one is pipette. Anytime you see the word volumetric in front of it, it means it measures only a single volume out. So what does this mean here? There's a line. You can't really see this one. I'm not going to talk about this one. I don't use that one. There's a little line here. That's where you would pull up a solution and you would have it at this line, and the meniscus would be at the bottom of this line. Now, pipettes are a single volume. So if you needed 10 mils, you would have to look for a 10 mil pipette. You would have to look for a 50 mil pipette. They give only a specific volume out, and it's very accurate. So you have to make sure, and it's also harder to use. Students have a hard time using these because they're kind of awkward to pull up the volume. So they're only accurate if you follow directly how to use them. A barrette. A barrette is what the second part of this lab you would use if this was in person. A barrette is very long cylindrical glass, and there's different volumes as well that you can use. The one that's showing in this picture is a 50 mil. It's zeros at the top, 50s at the bottom, and it's got a high volume of accuracy as well. They basically serve the same purpose as a pipette. Zeros at the top. So when you fill this up, you're going to fill this all the way up, and then you are going to never leave it start at 0. You always want to start with an actual measured number here, and then wherever it stops, that would be your final volume. So for instance, let's say that my initial volume was 1.35 and my final volume is 20.00. I would take my final volume, which would be the 20.00, and subtract it from my initial, and that would be the volume that I used. So if I would start up here, it would now end here. This volume that would now be gone would be the volume that was used in the experiment. And you can see here's a 50. This one would be a 50. It would have some labeling up here. There is a stopcock. That's what this orange thing is here. When it's horizontal or laying down, it's closed. And when it is open, it's parallel with the barrette. That means it's open and the volume is allowed to flow through it. Because it's a high volume accuracy, you want to make sure that there's no other things in the environment that could affect it. For instance, a ring stand. If the ring stand wobbles, this is not the way you want to go to keep everything. It's not going to be. So you want a ring stand when there would be a clamp here, and you would, where's my little arrow? A clamp here, and you would put the barrette on it. If the ring stand it wobbles, you want to immediately look for another ring stand or a larger base. There's two of the problems that tends to happen, and students don't always realize this, and they go forward, and that's not how you want to keep things accurate. It should be stable, not wobbling, so that you can really pay attention and read this and not have, you want to just basically reduce errors that could cause problems in your experiment. Next thing is how to read them. A lot of students have a hard time reading rulers and graduate cylinders and barrettes. You guys get confused with sig figs. I'm going to try to break it down as easy as possible. So let's see if what I'm doing this works. You first look at whether it's a ruler, graduate cylinder, whatever it is. Take a look at the numbers and determine what the increments it's broken into. What do I mean by that? Take an 18, for instance, and take the 19 and figure out what's broken up. So in between here, there's obviously some numbers that are larger than 18, but smaller than 19. So that means that this might be, based on what I see here, there might be increments of 0.1. So 18.1, 0.2, 18.3, 18.4, 18.5. Now that I know the increments, so this is increments of 0.1. Because 0.1 here plus 0.1 is 0.2, 0.1, add another 0.1 is 0.3. Hopefully that makes sense. Now that I discover what my increment is, you always add one more digit past that. And that's it. It's not that difficult. You just have to make sure that you are reading what the increments are correctly, and you'll be fine. So how do I make this work? Well, it's easy to, let's take a look at this one here. This is 21, we go to 22. Now we're at 22, all right? And you can barely see, I had to blow this up. There's an increment here, that's 0.1. This is an increment here, that's 0.2. It ends at the bottom of the meniscus at 0.2. So I always have to go one more increment digit out. So it's 22.20. This is my estimated digit. This is the one that's going to be, if let's say it was a little lower, a little higher, and there's no increments there, we're going to have to guess what that is. So basically, to make life easier for yourself, figure out what the increment is on whatever it is that you have to use, and then go one digit past. And that's it. It's really not more difficult than that. Always look at it as eye level as well, because this is a perfect picture telling you that if you don't read it right, or you're not at eye level, you're going to get different measurements. And again, that's going to mess up your experiment data. If we were in the lab, you would have a little card or get a white piece of paper to hold behind, because these are very hard to read at times. And that's going to allow you to be able to read the concave better. This is one I found. It's kind of blurry, but I found it online. Somebody broke down all the increments. So on this one, it's 0.1. It might be more increments depending, or less increments. You just got to figure out and read it and take your time to break it down. But this one is at 0.1, so you can see all these little lines. But now, so let's see, this is at 0.5. But I told you these are increments of 0.1. You need to go one more digit out, and it would be 0. But let's say we brought this little down here. There's no numbers here. This is the estimated digits. So this is why you always take it down one more number. So this would be, let's say I had it right here. So I would say it would be 17.55. There's nothing here to help me. So I would just kind of have to figure out where the distance between those are even. Balance. In your PDF, it discusses a balance. If you were in the lab, you probably went into the balance room, and there was some analyticals that look like this, and there was a digital scale that looks like this. One of the main differences, this one's more accurate than this one. Why? Because you can see all the numbers after the decimal. This one only has 2. That's the big difference. This one is enclosed to prevent wind and air and everything else, vibrations, to determine what the actual mass is. Now, this is the interesting thing about LabFlow. The PDF tells you a certain way to weigh out an object or a sample. And then here's a hint. On your quiz, you may be asked to do it a different way. So basically what I'm saying is that they give you instructions on how to do it one way, and then on the quiz, they ask to do it another way, but they don't have that listed in the PDF. So I am giving you instructions on, and you need to pay attention to, there's my hint. There might be a question on balance, and what I'm going to put on my PowerPoint is the what is being asked and not on the PDF. I don't know why. So what is the 2 ways? The original way, if you were in a lab and you have to share these balances, is that you would hit tare, which is the 0. It would 0 it out. You put your beaker, you would get a mass, you would write down mass, and then you would leave. And then you would use the same balance when you had your sample in it, and then weigh it, and you would subtract the beaker. What's being asked is my way that I put up here for you, and it's completely different. I work in a lab, and I am the only one that uses the balance at the time. So I can actually do mine a different way and avoid subtraction. I can get my beaker, I can place it on the balance, hit tare, and what it will do is it'll subtract the balance and show 0. I mean the beaker. It'll subtract the beaker and show 0. So I can take the beaker away, I can add my sample, place the beaker and sample on the pan, but because it's already subtracted my beaker, it is going to only give me the mass amount. But this is not something you can do when you share beakers with class, but I work in a lab and I'm the only one that uses it. So I can take my beaker off, walk away, not do anything to it, come back and use it again. When you use a balance, you always want to make sure it's clean. So you always want to clean it. There should be brushes, like they look like paint brushes to clean them off, because you don't want anything else on your samples, your equipment, whatever it is. It can cause impurities and your lab can go wrong very quickly. And if there's ever any problems, you should always notify an instructor. All right, in the last part of your PDF, it jumps straight to a percent error. This is the final part of the lab. You're going to determine the percent error based on the different glassware equipment you used in the experiment. And then you're going to compare those values. So we'll come back to this, but I wanted to give you the equation. Equation 3 is the one that we would be using. And this one says yield, but really it's the same thing. And I put this up so you can actually see a sample problem using it. That's all. Experimental is exactly what it says. It would be what you did in the lab. An accepted value would be a value that would be given to you, and that's going to be taken as the correct value. Density, the amount of matter is mass, and the space it occupies is volume. And with those 2, we can calculate the density of matter. I'm not going to go too much into density because it's part of your reading, and this is a review. So if you have problems with it, again, I suggest to take up things that I brought up earlier, textbook, reading, YouTube, so forth. If you need help, come and contact me. We can work this out together. Okay, so these are the formulas that you're going to be using in the lab today. So what is the goal of this lab? The goal of this lab is basically you're going to have 2 different chemistry glassware equipment, and you're going to go through the same lab with both of them with an unknown liquid. You're determine the density of this unknown liquid using different glassware, and through calculations, you're going to determine a percent error. Compare those values, and there's a question at the end. That's it. It's not that bad. Okay, so this is the first part. I put this together. It may not match a PDF. It may not match LabFlow, but these are my data points to help you understand how to do this lab. I have changed values. The only thing I did not change is sig figs. Whatever sig figs that you see on here is sig fig values that I got right. I don't have a key because all you students should have different data points. You should not be given similar ones. So I don't know if that's why I don't have a key. So this is something, when you guys don't like these labs, you should know that I go through each lab about 20 times because I'm trying to make sure, and I have to go through them just like you guys do because I don't have a key. And I go through them until I get everything right. And one thing I've discovered about LabFlow, Sometimes the sig figs do not match what they're given, and I don't know why. I have students that go with their own calculations and they get it right, and they don't use the same sig figs as me, and then I have students that do. So basically my answer is this: I don't know that. Obviously, if you look, you can instantly tell my sig figs don't match, but this is how the values that I got it correct with. If I had a key, if I had more information, I would help you, but that's just, I'm giving you the value, the sig figs that allowed me to get everything 100%. Now, that doesn't mean if you look at it and you have used the correct sig figs and you get it wrong, then it might be something else regarding your numbers. It might be a calculation numerical error. But for me, I use these sig figs digits. I got it right. I did change the numbers, so my numbers will not match on LabFlow, but they're pretty consistent with what was given to me. Okay, so first one, this is using a graduated cylinder. This should not be capital. My first trial, I listed as A and B because these are what we're going to do the calculations on. My first trial is 18.307. That involves my graduate cylinder, which is the mass here, and my 10 mils of unknown liquid. So by subtracting them, I now have my mass of my unknown liquid. That's what I need for density. Remember, density is grams over mils. I am given my volume of mils, and I simply set them up. So through subtraction, I discovered that my mass of my unknown liquid is 9.850 grams. Set it up over the volume, and I come out with my density being this. Again, sig figs don't match. There's not much more I can tell you about it. But that's my density number, okay? You have to take the average, which is why I've done 2 trials here. 2 trials matches the number here. If I had 3 trials, then this number would be 3. A lot of this, you guys are coming in with a certain amount of math that should be known or completed. So there's certain things that I will jump over because I expect that you already understand that. And if you don't, then you need to contact me. You need to get an old algebra book, look some of this stuff up because you're going to have a hard time if you don't retain some of these things. Okay, so here's my average for my measurements using a graduated cylinder. So this is my average density. The next one, we used a barrette, and temperature is listed here. That's going to be asked in here. Initial volume was 1.69. My final volume was 8.35. So this volume is final minus initial will give me my total volume used for that trial, which was 7.290. And it's giving me my mass of water. So I set this up. I did not put the calculations on this one because it's similar to the first one. Grams over mil. So I take my grams, I take my mil that's here, and it's going to give me my density. Again, I take the average, gives me my average for a barrette. Next one is where the percent air. We want to determine the percent air using different glassware and then compare the two. So I brought over my the equation 3 that was given to you. And with the graduate cylinder, I take my average and I plug it into the value that's been given to me. This is the accepted value, and I plug that in. And I end up with just a little bit less than 1%. With the graduated cylinder. So 0.9569. My barrette, plug that in same way, use the same accepted value, and I have a 0.7165. So if you look at percent errors, this has a lower percent error, not by much, but it's got a lower percent error than my graduated cylinder. Now keep in mind, I created these numbers, so my numbers may not reflect your numbers, and they shouldn't be. What you need to do is go by your calculations and don't worry about what you see on mine, okay? Then at the end, you have a question. This question is interesting because it gives you the question answers. So the question provides options, and those answers are listed as with numbers. So they're listed as option 1, option 2, but then when you get to answer it, they only have letters. So I'm putting this little legend here so you can see what they match up to. And you're going to answer this question based on what you see between these 2% values. And that's it. That's the end of the lab. So it's not a bad lab. Shouldn't take you that much time, hopefully. But if it is, this is where I want you guys to start posting on discussion so you guys can help each other come together. I don't have a problem with people helping each other. Don't provide answers with no content. That's cheating, and you'll get a 0, and so will the person that takes it from you. But if you actually communicate and give suggestions on how to solve something, I don't have a problem with that. You guys all have different data points, different data for the labs, so that shouldn't be an issue. Another thing I want to point out from when I used LabFlow last semester, I have found that this legend doesn't always match up. Because I go through the one lab so many times, I have found sig figs are incorrect and this little yellow marker doesn't come up. It'll mark it just wrong. So there's a lot of different weird things with LabFlow that I'm learning. If you guys understand LabFlow a little better, if you had an instructor that's maybe more familiar with it, send me an email, give me some information. If not, these are just a few things I'm telling you, because out of all the labs, I've never seen anything come up except for correct answer, or incorrect answer, and nothing else. And I've purposely gone through with different sig figs, and it's never given me that option, but it's marked it wrong. So that's it. Hopefully this lab is not too bad for you. This is the end of the lab. Have a good evening.